Hi. Welcome back. In this lecture, we will work out the solutions of the problems given in assignment 2. So the first problem was this was in groups and subgroups. So problem 1 was that if you had two subgroups H and K, if these are two subgroups of G, such that HK was equal to KH, okay, in that case you have to show that HK was a subgroup of G. Okay, so this was the problem. Now, what is HK or KH that was given, that was defined in the problem? It's just the product of the elements of the two subgroups. So in other words, HK was the product of elements from capital H and elements from capital K, which I will respectively call small h and small k. And of course, product means the product, the binary operation that was there defined on G. Okay, so I may sometimes, as I said, omit this dot here, but it's understood that we're using that binary operation dot, where H is an element of capital H and small k is an element of capital K. So this was the definition of what HK was, and similarly for KH is the other way around. Okay, if G is not commutative, there is no reason to think that HK would be the same as KH. Okay, this is true only when G is commutative. Okay, so KH, they were all elements of the form, same thing, but reversed. The order of the multiplication is reversed. Okay, so because each HK may not be equal to KH if G is not commutative, then there is no reason to think that HK will be equal to KH. But in this problem, it's given that let's say HK is equal to KH. In that case only, you can show that this HK, which is really a subset now, subset of G, will become a group of G, a subgroup of G with dot as the binary operation. Okay, so let's just do that. Okay, so let's do things one by one. The question is the identity element in HK? Well, H and K are subgroups. So the identity element, which I'm calling 1 again, okay, this is there in both H and in K, right? Because they are both subgroups. So if 1 is there in H and 1 is there in K, the 1 from H and the 1 from K, because HK means all multiplications of all elements from H and all elements from K. If you take the 1 from H and the 1 from K and you multiply them, of course that is 1 because that's the identity. But then that is an element of HK because this one is an element of H and this one is again an element of K. So the identity is there in HK. Okay, so that's pretty clear. Okay. What about the closure? Okay, this was very easy, so that's why we did this first. What about the closure? Okay, if I take an element H from capital, or if I take an element A and B, if two elements A and B from HK, will the product AB be in HK? That's the question. Okay, A dot B, that is. Okay, will this be in HK? Well, if A and B are elements of HK, then A should look like some H1 K1 and B should look like some H2 K2. Okay, because A being an element of H should look something of this form. Okay, right. So in that case, the question is, will A B, that is H1 K1 times H2 K2, will this be an element of HK? That's the question. Okay. Well, now there's something that we can do. AB can be written, of course, in this form because each A and B are like that. Now, because we're dealing, these are elements of G, of course, and G is a group, so we have associativity, so we can put our brackets the way we want. K1H2, well, that's an element of KH. Okay, K1H2 is an element of KH because there's a K first and then an H second. But they're equal. Okay, KH and HK as subsets. This is a subset of G and this is a subset of G. So they're equal. So if K1H2 is an element of KH, it must be an element of HK because these two are equal. So if K1H2 is an element of KH, but that is equal to HK, so K1H2 is an element of HK, so that should be written in the form that elements of HK can be written in. So being an element of HK, it should take the form, let's say H3K3. That's what it means to be an element of HK. Okay, so therefore this can be written as H1, I'm replacing K1H2 by H3K3 and K2. Now again by associativity I can sort of bracket out these two groups. This is an element of H because both H1 and H3 are elements of H, and H is a subgroup, so the closure property holds. So H1 and H3 is an element of H. This is an element of H. And similarly, this is an element of K because K is also a subgroup. So if you have an element of H and an element of K multiplying, that should be an element of HK. Because that's what it means. This is the first element is from H, is like this, some H, and the second element is from K. And so the closure property holds. So the answer is yes, it is true. Okay, the closure holds. What about associativity? Of course, that holds because associativity is just carried forward from the mother group. Okay, so associativity is true. Okay, that we don't have to check because it's just that it inherits that property from G. Okay, what about inverse? Okay, so what about inverse? If A is an element of HK, will A inverse be an element of HK? That's again the question. Well, if A is an element of HK, then of course as before, it should look like something, a product of H and K. But then A inverse is the HK inverse, which really is the K inverse H inverse. But K inverse is an element of K because K is an element of capital K and K is a subgroup. So if K belongs to capital K, K inverse must belong to capital K because the inverses belong to a subgroup. Similarly, H is an element of capital H and H is a subgroup, so H inverse must belong to capital H. So therefore, this is an element of capital K, this is an element of capital H. So really, this is an element of KH. Because the first element is from K, the second element is from H. And so, but they are equal. So therefore, this must be an element of HK again. And so I can write it in the form of H1K1. Don't think of the same H1K1. I was writing H1K1 for A here. If you want, you can write that. Okay. Then let me write something else. Then it should look like some H4K4. Okay, because this is an element of HK. Okay. Well, if that's true, and then the answer is this is an element of HK, and so A inverse is an element of HK, and so the inverse property holds as well, and so this turns out to be a subgroup, and that's your first solution. Okay, let's go to the second one. The question was, The question was, there were two parts. We were looking at the first part of this was you had to show that NZ with addition was a subgroup of Z with addition. Okay, set of all integers Z. NZ is the multiplication of, NZ really is given. NZ meant n times any A, for any integer A. Okay, you have to show that this was the subgroup. Okay, let's just do that first. It's very easy. First of all, what's the identity here? What's the identity in Z? It's addition. So the identity in Z is 0. That's the 0 is the additive identity. Okay. If 0 is the, so we're doing for identity. If 0 is the additive identity, the question is this identity present in NZ? Because if NZ has to be a subgroup, then it should possess all the, it should, satisfy all the axioms of being a subgroup, and identity is one of them. The question is, because 0 is an element of Z, so n times 0 is also 0, okay? And n times 0 is an element of NZ, so 0 is an element of NZ, so the additive identity is there, okay? What about closure? Closure. If I take an element A and B from NZ, then will the product be in NZ? If A isn't from NZ, then A must be, well, I'm using A here, so let's write XY, okay? XY. Then X must be of the form sum n times sum A, and Y must be of the form n times sum B, where A and B are integers. That's what it means to say X and Y are in NZ. Okay. Well, then what is X plus Y? Because remember, this is addition. We are using addition as the binary operation. Well, that is NA plus NB, but you can take N out, that is A plus B, and A plus B is an integer. So again, this is in this form where you have N multiplying some integer, and so therefore A plus B has to be an element of NZ. So that's the closure property. What about the inverse? The inverse is if X is an element of NZ, what's the inverse of X in Z? It's minus Z. It's negative of Z, because we're dealing with plus, which is the additive binary operation here. So what is minus X? So X really is NA of this kind, and minus X would be N times minus A. But if A is an integer, then minus A is also an integer. So again, this is in this form. So this has to be an element of NZ. So X belongs to NZ would mean that minus X is an element of NZ. So the additive inverse is also there. Okay, and finally, associativity again. It's inherent from the mother group, okay, because everything here is associative. You can play around with your brackets here, so you can do the same thing with this, because all of these are elements of this. Okay, so that's a subgroup. The second part was to show that if A and B are two integers, okay, then n, this integer n, or this natural number n, okay, would divide A minus B if and only if A plus nz was equal to B plus nz, okay. Now remember, these are two cosets, okay. Nz is a subgroup, okay. So we had, if H was a subgroup of G, then for any element G in capital G, GH was a coset. This was a coset, okay, where this meant G dot, okay. But of course, here we are using addition, Okay, and G, this is the mother group, which is Z here. And H is this NZ, which we have just proven to be a subgroup. If we take H to be this NZ and G to be capital Z, then what we have here is, and of course this dot here means addition, because that's the binary product, that binary operation that we're using. So any element of this, so what would be, so if G is an element of Z, in other words it's an integer like A, okay, then what would GH look like? It would be G plus, because we are substituting dot by addition, because that's the binary operation, plus what's the subgroup? It is NZ. Okay, so A plus NZ is really a it's a coset. It's a coset of NZ, which is a subgroup of Z by this element A in Z, with plus as the binary operation. Okay, similarly B plus NZ. Okay, so the question is, this will divide, N will divide A minus B if and only if these two left cosets are the same. Okay, so let's just see one by one. I mean, there are two sides to this. If and only if means there is a necessary side, there's a sufficient side, the forward and the backward. So if this is true, if N divides A minus B, what does that mean? It means that A minus B is equal to some multiple of M. Okay, there's some number, some integer here which will multiply N, and that's the only time if you divide this by N you will get M. Okay, but that's an element of NZ, isn't it? That's what it means. M is an integer, N times an integer is an element of NZ. And this just means that, remember when two left cosets were the same, in product terms, the two left cosets, G1H was the same as G2H if G1 G2 inverse were both elements of H. Okay, if this was true, if G1, G2 inverse, whatever, I mean G2 inverse G1, you can write the same thing because this is a subgroup. You can, here it was G2 inverse G, I think that's what we had. G2 inverse G1 was an element. Okay. The question is, what is G2? So let's say G1 is B. We're talking in terms of this now. H is of course NZ. Say G1 is B and G2 is A, and of course there is a plus over here. Okay. In that case, what's G2 inverse? It's minus B, right? Because inverse is the inverse with respect to the operation. Because we are using plus as the operation, the inverse is minus B. Okay. And this means plus, because the dot here means plus. Plus, what's G1 is A, okay. These two will be equal if this one, that is A minus B, is an element of H, which is true. Okay. This tells us A minus B, so this is what it is actually. So let's just go over this. This really is the G2 inverse minus B. Okay, and A really means the G1. Okay, if you want, you can swap their places as well. I mean, this can be written as B minus A and N times minus M. That's also true because minus M is an integer. Okay, you get that from here as well. Okay, so this can be written, sorry, minus B. Oh, sorry, it's the same. So I'm writing minus B and A. I'm sorry, not changing signs, just swapping their positions. So minus B and A is fine. This is G2 inverse. this is the product, the binary operation, which is plus here, and A is G1, okay? And this, because this is an element, so therefore this is an element of H, and because this is true, therefore the two cosets G1, the two cosets by G1 and G2 must be the same, and these are the two cosets by A and B, which are G1 and G2 respectively, and so therefore this is true. Okay, I hope that's clear. This divides, you have to translate our notation in product form to this notation in addition form. This means what's going on in terms of product is this, okay? This n divides this means minus b plus a is an element of nz, and this really means minus b means the G2 inverse, and a really means the G1, and the plus really means the product. And because this is an element of, because nz is h, so therefore the two left cosets must be the same, okay? But here G1 is a and product is addition, h is nz, so G2 is b, product is addition, h is nz, so this is true. The two are the same as left cosets, okay, when this is true. What about the other way? Okay, when is the other way true? Okay, let's show that. Suppose this is true. Suppose a plus nz is b plus nz. So they are the same as left cosets. They're the same as left cosets would really mean that a minus b, okay, has to be an element of nz. That's what it means. If the two are the same as left cosets, then G2 inverse G1 should be an element of H. Okay, that's what it meant. We've done this many times before. These two are same as left cosets would mean that this is true, and this is really this, with minus b written first. Okay, same thing. If you want, I can write it like that. So this is true, so this is true. And this is true means that minus b plus a is n, this is an element of nz, means it is n times something, as we have written before, m. Okay. And so this is really a minus b. And so a minus b can be divided by n, because if you divide this by n, you will get m. Okay, so this other way is also true. Okay, just a simple, back and forth way of looking at the same thing. Okay, all right. What about the third problem? Is about to show that conjugate of a subgroup is also a subgroup. Okay. This was one of the things that we had mentioned in passing while doing while we were doing normal subgroups and kernels. So okay, so this is what it is. So K is a subgroup of G. We have to show that small g is some element of capital G. We have to show that this is also a subgroup of capital G, where small g is an element of capital G. Okay, this is the conjugate by small g, conjugate of capital K. And of course, you remember what this was. The conjugate meant that you multiply small g and small g inverse on both sides to all elements small k of capital K. This was the meaning. Okay, when is this a group? Well, first of all, is the identity there? Well, the identity is there in K because K is a subgroup. So if I pick the identity from K and I multiply G and G inverse from both sides, so G identity, G inverse, because now this is an element of K. So this is an element of the conjugate. Okay, this is an element of the conjugate because small 1 is an element of capital K. And now 1 has no effect on any of them. So this is really G times G inverse, and that's just 1. So 1, which can be written like this, then, and because this is an element of the conjugate, 1 becomes an element of the conjugate. Okay, so the identity is there. Okay, what about closure? Can I take two elements from the conjugate? They will look like G K1 G inverse and G K2 G inverse. Okay, two elements from the conjugate would look like this. If I product them, this and this, will that belong to the conjugate? That's the question. Well, if I product them, I can first operate G2 G1 G inverse G by our rule of associativity, and this will reduce to 1 in between, and 1 again will have no effect on the product. So this will become G K1 K2 G inverse, but K1 K2 is an element of K because both K1 and K2 are elements of capital K and K is a subgroup. So by closure property, this must be an element of capital K, and so this can be written as an element in the conjugate, and so this has to be an element in the conjugate. All right. What about inverse? If I take an element from this conjugate, if I invert it, well, I will, I will sort of go, reverse the positions of the elements with an inverse sign. That's what it means. So I will have G inverse, K inverse, and G inverse. So this G comes here with an inverse, the K remains in the middle with the inverse, and G inverse comes in front with the inverse. But G inverse is just G, and this is K inverse, G inverse. But small k was an element of capital K, so K inverse must be an element of capital K because capital K is a subgroup. So, and we are back to this form of an element in the conjugate, so this has to be an element in the conjugate. And of course, associativity is again true because this is a subset of G, and I can throw around brackets anywhere here because these are all elements of G. Okay. All right. So that's a very easy one. So conjugates are always subgroups. Let's do number 4. Number four is a question in Lagrange's theorem, really. It says that G is a group with order P, which is a prime number. Okay, it's a prime number. You have to show that G is cyclic. Okay, in other words, G can be written as an element which as a group which is generated by an element like this. Okay. All right. So let's take an element A from G, okay, which is not the identity. So when I say that this is prime, obviously prime has to be at least 2. Okay. So it means that we don't count 1 as prime. So at least 2. So it means that it has more than one element. So it has more elements than just the identity element. Okay. So G is more than just the identity element. So you can find other elements. So I'm taking an element which is not equal to the identity element. Okay. I'm taking an element which is not the identity element. And I form this subgroup. Remember this subgroup where you square, cube, where you take all the powers of A. This turned out to be, and also the 0, which was the 1, which was the identity. Okay. So if you take all powers of the element A, this turned out to be a subgroup of G. Okay. We had done this when we were doing cyclic groups and subgroups. Okay. And now this is a subgroup. So this really is a subgroup of G. And by Lagrange's theorem, the order, or we're writing order like mod here. The order of this subgroup should divide the order of G. Isn't it? Lagrange's theorem. We've done that whole proof in the assignment. The number, in other words, order means what? The number of elements in A. Okay, we're dealing with finite groups here because the order is, the number of elements in G is finite. It's a prime number. So the subgroup, which really is a subset as well, is a subset of G. So this should be a finite set as well. So the number of elements in A, in this cyclic subgroup A, should divide the number of elements in G by Lagrange's theorem. This is by Lagrange. But this is P. In other words, so what can divide P? What can divide a prime number? Either the prime number itself or 1. Okay, but we don't mean this is 1. This is not 1. The number of elements in this is not 1. Because by choice, we have taken A to be something which is more than the identity. Okay, if this was the identity, then it would be just 1. Okay, then the number of elements would just be the identity and it would be 1. So by our choice, because we have chosen A to be something which is non-identity, therefore the number of elements in this subgroup should be more than 1. So it's not 1. So that means automatically that the number of elements must be equal to P. Because these were the only two possible factors of P, if this had to divide P. But then, if that's the same as the order of G, so a subset has the same number of elements as the mother set or the superset, and so the two should be equal. Okay, if you have a subset of a bigger set, but the number of elements in the two are the same, the two elements should be the same. Okay, and so therefore, by that logic, this can be written as the cyclic subgroup form of generated by an element A, and so therefore this is cyclic. Okay, that's number 4. Okay, let's just quickly do 5, number 5 and number 6. Number 5 is, hi, sorry about the cut. I sort of ran out of space with my recording. So anyway, let's just get back to problem number 5. So we were supposed to show that if n is a subgroup of G, then these two conditions were necessary and sufficient conditions. If this is true for all G, if in other words, if n is normal, okay, then you could also write the condition, this conjugate being equal to the subgroup itself. That condition can be rewritten in this form of the left coset being equal to the right coset. So let's just do the necessary condition first. So let's just go forward. So assume that this is true. We have to show that the two left cosets are the same. So first I'll take an element from capital Ng, which is the right coset of capital N by G. So take small ng from capital Ng. Okay, I have to show that this is an element of Gn. Now, what I can do is first, let's look at this element G inverse Ng. Okay. Now, this is true. This condition is true for all elements G in capital G. So, in particular, this is true when G is G inverse. In other words, G inverse capital Ng is equal to N. Okay, I hope that's clear. This is true for all G. So if you take, instead of G, if you take G inverse, then also this condition is true. So let's just plug in G inverse for G. So you have G inverse instead of G here, and here you have G inverse, which gives me G. So this condition is true, okay, if this is true for all G. Okay, now this therefore, now as you can see, this thing is an element of this conjugate by G inverse, okay, and so this is now of course this is equal to N, so this must be an element of capital N, okay, and this being an element of capital N means that you can write it as some n1 in capital N. Okay. Now, if this is true, then what happens is that if you multiply both sides, or you operate on both sides by G from the left, then what you get is, so you have a G with G inverse, which will give you identity, which has no effect on Ng, so it will keep Ng as it is. And on the right, you would have this G over here with an n1, and that's an element of the left coset of n by small g. So we started with an element of the right coset, Ng, and we found that Ng was an element of the left coset. So therefore, the right coset must be a subset of the left coset. Okay, and similarly, you can show the other way. If you start with an element Gn from the left coset, okay, then of course then we can stick to Gn G inverse. Then Gn G inverse being an element of this conjugate, which is equal to n, so this must be an element of n. So this you can write as an n1 from n. Okay, and now again you can multiply on the right of both the sides by G. So G, you get an n1 G on this side, and the G on the right eliminates the G inverse here, and so you get Gn. Okay, and that's an element of the right coset. Okay, so you started with an element of the left coset, you get that element to be an element of the right coset. So again, the left coset is the subset of the right coset, and so the two are equal. Okay, you can do that exact same thing for this side as well. I mean, remember, this was one of the conditions, that in order to show that this is true for all G, all we have to show that the conjugate was a subset of n. Okay, this is one of the points that we mentioned while we were doing normal subsets. Okay, to show that the conjugate of a subset of a subgroup is equal to the subgroup itself, it's enough to show that the conjugate is a subgroup, it's a subset of n. Okay, and then the other side holds as true as well. So we'll just do that very quickly. We just show that this is a subset of n, and then that means that this will be equal. Okay, so let's just assume that this is true. We are doing the other way now. Then an element of this should look like Gn G inverse. Well, now Gn, okay, we have to show that it's an element of capital N. Okay, so, well, how do we do that? Look, Gn is an element of this Gn, okay, this left coset, which is equal to the right coset. Okay, so this element, this element, therefore, being an element in the left coset, should be an element in the right coset. So this can be written as n1g, because this is an element in the right coset, and elements of the right coset can be written like this. And then you have this G inverse here outside. So the G and G inverse will give you identity, which will act on n1 to give you n1, and that's an element of n. So you started with an element of the conjugate, and you get that to be an element of n. So the conjugate is really a subset of n, and that's enough to show that the other side is also true. Okay, so that finishes problem number 5. Both the necessary and the sufficient conditions are true. All right, so we'll just finish off with problem number 6. Problem number 6 said that suppose H is given to be a subgroup of G, and here what we define is the what is called the index. Okay, index of H in G. It's written like this. Okay, it's just the division of the number of elements in G by the number of elements in H. That's whatever number you get. This is by Lagrange's theorem again. Because H is a subgroup of G, the number of elements in H will divide the number of elements in G, and whatever number you get, that we call the index. Okay, this is called the index of H in G. Okay, now the question is, suppose the index of H in G is 2 for a particular subgroup. Show that H is a normal subgroup of G. This is what you have to show. So the index is 2, show that it must be a normal subgroup. Well, if the index is true, so really, if you remember again, if this is G, the entire set G, then whatever this number was, if, all the cosets, all the left cosets, for example, of H had partitioned G into these disjoint sets. Remember, so these had to be all left cosets. For example, if I'm talking about left cosets only, so left cosets could either be equal to each other or they would be absolutely disjoint. So therefore, they partitioned them. So the number of left cosets in G, number of left cosets of H in G, for example, would be equal to the number of partitions here. And that's given by the whole number of elements in G divided by the number of elements in H. Okay, actually these are all same size because the cosets would be of the same size. Okay, so the number of partitions here is the same as the number of cells, for example, would be the same as the number of cosets H would have in G. Okay, that's what it means when you divide the number of elements in H, the number of elements in G by number of elements in H. Okay, so therefore, so what this index really tells us is number of left or right cosets of H, for example, in G, that is equal to the index of H in G. That's what it means, okay? Right? I mean, it's just a simple concept of having, if you have a bag of oranges, for example, and the bag weighed 30 kgs and each orange weighed 6 kgs, then you would know that there were 5 of them, okay, 5 of those oranges in there, okay. Well, oranges wouldn't weigh 6 kgs, but whatever, okay. So that's the same thing, okay. If you divide the number of elements in G by the number of elements in H, it just tells you how many left cosets or right cosets of H are in there, okay. So because each coset has the same number of elements, so they really have the same weight if you think of it that way. So the number of left cosets or the right cosets will be given by the index, but in this problem the index is given to be 2, so there are only 2 left cosets or 2 right cosets, okay. So if I list the number of left cosets, for example, what are the left cosets? One is H itself, because H multiplied by the identity, you remember, that was one of the cosets. H itself as a subgroup could be represented as a coset because if you multiply 1, and they would multiply 1 with it from the left, and there would be something else, okay, some other, say, G H. Okay, so there would be two left cosets, and the two right and the 2 right cosets would be, well, there would be 2 right cosets. So HG1, for example. Okay. The question is, can HG be the right coset? Okay, the right coset which is not the identity coset or not H. Okay. So if this is true, then HG will be equal to GH, okay, and you would have that condition, HG being equal to GH, and that's the only right coset and the left coset other than H itself, and so H would become normal, okay. The thing is, if G is a coset which is not H, then small g cannot be an element of capital H. Okay, it cannot be. I mean, if you think about it, if G was an element of capital H, then GH would mean that you're multiplying all these elements where H, okay, because all these small h's are element of capital H, but G is also an element of capital H would mean that this product is an element of H, so this would really become H, okay, by closure property, because H is a subgroup. So to say that GH is not the same as H, G cannot be an element of H, otherwise the two would be the same, okay, by closure property, okay, because these are all elements of H then. Okay, and as two cosets should have the same number of elements, so the two would be the same, and that's a very straightforward argument. So G cannot be an element of H. Okay, by the same logic, here if you look at HG, if G is not an element of H, then HG cannot be H. Here, because if HG is H. For example, if HG is H, then that would mean that G is an element of H. Why? Because 1 is in there, H is a subset. So 1 is in there, so 1 would get multiplied by G. So this is an element of HG. But HG is H, so this must be an element of H, but this is G. So if HG was equal to H, then G would be an element of H, which is wrong because from this one we have shown that G cannot be an element of H. Is that argument clear? Let's just go over that once more. We have two distinct left cosets. That tells me that G cannot be an element of H, because if G was an element of H, the two left cosets would be the same. So this is true. G cannot be an element of H. Come to the set of right cosets. I claim that the other right coset other than H would be HG itself, this G, okay? Well, I want to show that these two are not equal. Then you would have two distinct right cosets. If they were equal, then because 1 is in there in H, so G would become the same as 1 into G, which would mean that this is an element, G is an element of HG, because all elements of HG look like some H multiplied with G, and H means here 1, so G becomes an element of HG, but that's equal to H, so then G becomes an element of H. So if we assume that this is true, that these two sets are equal, then G becomes an element of H, which contradicts our assumption. Okay, so therefore, by this contradiction, we show that HG cannot be equal to. So these two are distinct as well. Okay, so if these are distinct, okay. And so these are the only two possible left coset and the right cosets of H and G, then I think we can easily say that 1 is equal to, these two are the same because they're both H. Okay? And the other one is HG, these two are the same, must be equal to HG, because, after all, these two together, all of them put together should give me G, because index of H in G is 2 here means that H just sort of divides G into two cosets. One of them is H, the other is GH. Okay. So if this H is the same as this H, then this GH must be the same as. So if you think about the partition by the right cosets, these two would be the same. The right coset by G will be equal to the partition by the left coset by G, and of course for 1 it is the same. So this is true, okay? And we know that this is true for all G, for whatever G you can find, okay? Because for any other G1, this is either this or this, okay? Because the partition is 2, okay? The index is 2. So we can only think of, we don't have to consider all the other left cosets because there are only 2, or all the other right cosets because there are only 2. But for these two elements, G and 1, this is true, and so that's the alternate, that's the alternative definition for a normal subgroup. Remember, if this is true for all G, or this is true for all G, okay? And we have shown that these two were equivalent. So by this logic, therefore, because this is now true for whatever G's we can consider, one is 1 and the other is G, therefore, this must be a normal subset, normal subgroup. H will have to be a normal subgroup of G. Okay, so that finishes all the 6 problems, and I hope something new to take away from all of these problems. Okay, we'll take things forward in the next lecture again. Thank you.